today we are going to our next topic, which is negative binomial distribution. So today we are going to understand what is negative binomial distribution, how it is different from geometric Bernoulli binomial distribution. So since it is already written like to get the waiting time for the RH success in repeated period. So let's see the difference between Bernoulli, binomial, geometric and negative. Bernoulli, you have only one trial of success or failure. For binomial, you can tell how many successes in fixed trial. And geometric, how many trials until you win the first. And negative extends the geometric. It's just like similar to binomial, but it is just reverse. Like binomial, like how many successes in fixed trials? Negatives, how many trials until the RH success? So you see the parameters. In Bernoulli, you have two parameters, N and P. In negative, you have R and P. I hope you understand. Let's start with a very basic. What's geometric? Our target is to get the first profitable trade in, which is zero point 0.4. So x equals to 4. But negative target is 3 profitable trades. If RH success occurs exactly on trial and the timeline is two structural phases. Yes, it's the negative of binomial. You just enjoy what I'm saying. It's probability, so if 1 minus this will definitely become the negative binomial. I hope you understand, you fucker. So let's derive its formula of probability mass function of this negative binomial. So we are start with NCR n minus 1 r minus 1. So into P r 1 minus P n minus 1. You see it is quite similar to the binomial distribution equation, but the difference is there were 1 minus P to the power r, but here is 1 minus P to the n minus r, which is a quite remarkable way to think. So let's execute this. Let's suppose you created a trading strategy and it is a probability of 40% of winning. So what is the probability it will get the third profitable trade exactly in the seventh trade? So our target wins is 3 and our trials are 7. So what is the probability? So you will put the formula 62.4 power 3.6.4 and it's 18% chance that you will exactly win third in the seventh trade. So let's also talk about the boundary condition, like how this model actually collapses, because it is necessary. It is not a sequential. It is a the geometric distribution that we earlier studied is just a special case of negative binomial when you put n minus 1 equals to 0, like the geometric function. So let's understand the expected value and variance, like what would be the mean and variance is just quite similar to the geometric and binomial, just r upon p variance r1 minus p upon p square is just like expands the timeline for intuition slides. Like higher the value of r, the required success will be longer, higher the probability it will compress the timeline, shorter the wait time. So higher the success, higher the wait time. Higher the success probability, shorter the wait time. So you get very given a simple example. If R is 3, P is 0.4, so e to the power x is 7.5, like average 7.5 and variance is 11.55. So let's talk about a real world benchmarks and profitable fallacy. Predicting frequency is the only half of risk management. Statistical average must be contextualized within the business parameter. Our target execution is, let's start with credit analyst screening application, like our probability of 0.2 that it will meet the criteria, and we have a target of 5. We need R of 5, so we calculate the average. So we will need an average of 25 reviews to fund 5 loans. The analyst warning: algorithmic trading with 0.55 win rate, wait for 10 waits, a 55% win rate guarantees occurrence, not profit. So it's an occurrence, not the guarantee. So let's talk about maths versus Python. The Python that will offset regarding this. A critical divergence exists because while creating the theoretical mathematics and computational implementation, failing to account for this offset invalidate algorithmic situations. Mathematical definitions, the target is like number of trials until the RH success, total length is n and x total, but the numpy is different. So we'll use numpy.random.negative binomial format, the number of failures before the RH success. So we are actually can't actually create in numpy, so that's why we are creating two section n minus r failures plus r of the win. So total tries is numpy dot random dot negative variable binomial rp plus r. It's just like quite similar, just to offset the mathematical part. So probability of success on a one trade, you can lead to geometric number of winning trades in 100 trades is simply binomial. Number of trades until first win is geometric. Number of trades until 10 win it's negative. Like you can crisscross match. So Bernoulli trials we have not learned for this thing. We actually explored a single cohesive system. The Bernoulli trial are successful, like counting successes, counting trials. It's just two different ways. It's just like two sides of a coin. So next is breaking the discrete value until one framework. We have a relied number of trials on number 7. So we'll also focus on the rare limit. And next our topic is Poisson distribution. So it's gonna be very interesting. So let's see you tomorrow in next video. But the next video will be a practice session of binomial, Bernoulli, and geometric, more like a puzzle.